Добрый вечер, добрый день, дамы и господа. Спасибо. Меня зовут Глеб Вдовин. Я представляю здесь университет города Делфта, а также лабораторию, которая была сформирована в рамках программы повышения конкурентоспособности между TU Delft и ИТМО. Вот, лаборатория называется «Интеллигентные оптические системы». Вот. Ну и теперь я обязан говорить по-английски, поэтому дальше я буду говорить по-английски. Thank you very much once more. And the topic is called Plenoptic WF sensor with a scattering pupil. I understand that, well, I have very little time here, like 15 minutes, so I'll try to be very, very brief, and I hope that you will be able to ask questions afterwards if you find the topic interesting. So the overview is presented on this slide, and I'll be talking about actually about wavefronts. I'll give you a very, very brief definition of a wavefront, and then I'll try to explain why we need to use to measure wavefronts and how we measure them, which conditions are very important to do that. Then I'll be talking about well, a very popular type of wavefront sensor, which is a Hartmann sensor. Very simple principle, so again, I'll tell you a couple of words about that. And then very naturally we'll see that a Hartmann sensor has some limitations. We want more, like for instance, if we measure wavefronts, we want to be able to measure wavefronts with higher precision and higher range. And therefore, we figured out that maybe we can use a little bit different configuration with a Plenoptic configuration, which is based on the measurements of light field. And with this configuration, we'll be able to overcome the limitations of Hartmann sensor. And then I have some very brief conclusion. So wavefronts. What is a wavefront? Well, there are different definitions for wavefront, and I'm sorry that it's not very high contrast here. Maybe because we have too much light on this side. Doesn't matter. So wavefront actually is a surface that corresponds to a constant phase, or if you want geometrically, you can define it as a surface that is orthogonal to light rays in the light beam. Now, what is important is that basically when you have a point source, you have only one wavefront, and usually it's a spherical wavefront. And then you need to have spherical wavefronts to be able to form images. And another thing is that if you have one wavefront, then usually you have image of only one point. So if you have extended object, then actually, well, you deal with incoherent light. And in this case, you, like for instance, if you look at my face, and you can see my face like with details, it means that you have many points. And each point is a source of a wavefront, which basically means that to be able to measure a wavefront, you need to say, well, I want to measure the wavefront from that particular point. So the definition of wavefront is somehow very closely related to the, well, to coherence of light. And when we measure wavefronts, we must be able to exactly tell what we are doing. For instance, in lasers, we have wavefronts of a laser beam, and at the same time we can have like something like m squared. And with this m squared, we actually may have many modes, and each mode has individual wavefront. So again, in this case, we need to say, okay, well, we measure wavefront only for this mode. Or otherwise, we measure something that we don't understand what we are measuring. So, well, this is very important to understand. And after that, I go to principles of how we measure wavefront. And we start with a very simple experiment. We just have an... Sorry about that. We have an aperture here. And if you have a wavefront tilt, in the input of the aperture, then we see that, well, the center of gravity of the light spot will move. So if we tilt it down, then the center of gravity will go down. And if we calculate this integral, we'll be able to calculate the tilt of the wavefront. And the rest is very simple. We just make many apertures. And in each aperture, we can see how the wavefront is tilted locally. And from these local tilts, we will be able to reconstruct the wavefront. It's very simple. And this is a Hartmann sensor. Now, for Hartmann shock, we replace these holes with micro lenses. And it allows us to use the whole aperture. All the light that comes to the sensor is used now. When you use Hartmann, we have holes, so not all the light is used. Now, here I have some examples of Hartmann masks. That's what you see. Actually, how do you measure the wavefront? You measure the coordinates of these spots, and then from the coordinates of these spots, you can define the tilts, and from that you calculate the wavefront. It's very easy. However, if you have a very strong deformations of the wavefront, then you have something like this. Something like this. Well, this is the initial situation. It's a good wavefront, it's a flat wavefront. And here you have just a lot of trefoil. Trefoil is a typical Zornig aberration, but, well, that's what you see. And basically, in this case, it's impossible to say which point goes to which location, because some spots are already merged together. It's a very difficult situation. And actually, you can write some simple formulas that will tell you that, there are some limits for Hartmann shock sensor. And basically, physically, these limits are very simple. Your wavefront is not measurable if two spots are coming together. Then, it's impossible to say where it comes from. So we need to have some kind of configurations that allows us to avoid that. And this is about the thin length, and I skip it because everyone knows about that. But it's important to understand for the next slide. We can have a configuration like this. In this configuration, we have a lenslet array that is placed behind our pupil. And each microlens in this lenslet array builds an image of pupil on a sensor, on a CCD sensor in this case. So basically, if we have some tilt of the wavefront in the input pupil, then we still are able to calculate the center of gravity of the whole beam. But since we also have separate images of the pupil here, then by combining certain parts of these images, we will be able to calculate the local tilts generated by parts of the pupil. Basically, we have exactly the same situation as in normal Hartmann shock sensor, but we do not have microlenses in the pupil. The problem is that if we have a single wavefront, then we have only one ray coming through each point in the pupil, which means that each microlens will build just one point image instead of the pupil image. In principle, we have a situation when we build pupil image here, but there is no light that allows us to do that. So we have some kind of a degenerate situation. In principle, this situation can be used to measure the wavefront, but it will not measure the wavefront just simply because, there is not enough rays going in different directions. And then you can very simply solve this by placing a scattering element in the pupil, like here. In this case, you have a single ray coming to the pupil, and this ray is scattered to many directions. And this happens for all points in the pupil, which allows us to build good images of the pupil on the sensor. And again, by combining parts of these images, we are able to calculate the local wavefront tilts in the pupil. It takes some time to understand how it happens, but when you understand, it's very simple. It's just like inversion of the Hartmann shock sensor. And what we say is the scatter helps a lot because it gives us so many different points illuminated. that instead of the original, the generic case, we have a very good case when we have many points illuminated, and then we can have very good signal-to-noise ratio. And here I just have some examples of experiment that we built, and with this experiment we really were able to measure wavefronts with this like inverted wavefront sensor. And just to finish my talk, I can say that this configuration does not have limitations of a normal Hartmann-Shack sensor, because all sub-apertures are actually illuminated the same area, and the separation between the sub-apertures happens already like in the Fourier plane. And by doing this, we can have extremely large range of measurement of local tilts that are present in the input of this wavefront sensor. And by doing that, well, we can just overcome as a limitation of a normal Hartmann-Shack sensor. About applications and some specifics, of course, Hartmann-Shack sensor, usually you have a microlens array and as a chip behind of about the same size. In this case, you need to have a rather little aperture for the input pupil, and you need to have a very large sensor behind, because you want to see all these tilts of all these rays that are coming to the input pupil. And basically, well, that's all I wanted to tell you. Thank you very much. I hope that it was not too long. Спасибо.
Спасибо большое. Это очень интересный такой позитивный и очень плотный доклад получился. Вопросы? Опять же, дополнение.
I have a simple question. As far as I'm concerned, there is also, in order to calculate this, the wavefront, you can use the transport of intensity equation.
Yes,
there is a method, right? You just get the intensities at a certain planes and then you backpropagate them. How does this compare to the sensor you have proposed?
Well, this is much more robust, because when you do intensity transport, you are very much dependent on the linearity, because, well, you measure intensity and you calculate the wavefront out of intensity directly, while here you calculate the wavefront out of geometry of situation. You calculate the centers of gravity, and centers of gravity are basically independent on the linearity of your sensor. You can have a gamma parameter of your camera, whatever you like. You can use webcam, and it will all work. With intensity transport, it's extremely difficult to get to a high precision. You may have extremely high dynamic range with intensity transport, it's no problem. And another problem is that, well, here you get some kind, in all problems of wavefront sensing, you have a problem of boundary conditions. You don't know what happens at the edge, because, well somehow information just disappears there. So in this case, you just use some kind of Zernike polynomials or whatever, and you just make a decomposition. And well, you are satisfied with the solution. So the problem of boundary conditions just does not pop up. While with intensity transport, just the form of equations that you need to solve requires you explicitly define the boundary conditions. And it's somehow a matter of choice, which is difficult.
Depends on the application. Thank you.
Depends on the application.